Well, all of you probably know Buzz Lightyear over to the right there, and I love this comment. It goes all the way back to '95, and I always wondered if this was inspired by cold fusion, where it says, are you still using fossil fuels, or have you discovered crystallic fusion? Over to the left, the joke is you made the cover of the Rolling Stone. Well, it looks like Pam and Frank and Stan made, if not the cover, the inside pages of The Economist magazine. So my outline is I'm going to talk about NASA's needs, how they're currently trying to meet those needs, discuss another road, and briefly go into the fast fission reactor, and then talk briefly about my space act with NASA. The players in this are JWK Corporation, GEC Corporation, U.S. Navy Space War Pacific, University of Texas, Austin Nuclear Engineering Teaching Laboratory, where I'm a research fellow, the NASA Glenn Research Center and Plumbrook facility, where I'm an experimental physicist, and U.S. Navy Surface Warfare Division Dahlgren, where I'm a PI. So basically, NASA needs electrical power. Right now, they get it from radiothermal generators, and on a good day, you get about a kilowatt electric out of it. Over time, obviously, that degrades, not so much because of the 80-year half-life of the plutonium-238, but because of radiation damage to thermoelectric converters. And if you look through what the real need is, well, the Space Mission Directorate for planetary probes would like 10 kilowatts electric. And I'll talk a little bit about the Krusty program, which is intended to do that. But if you get into the other division, Human Exploration and Operations Mission Directorate, well, they want planetary power. On Mars, to begin, at least 40 kilowatts electric. If you want to have a nuclear electric ion drive to get there a little bit faster so you don't get fried en route, you need 100 kilowatts electric up to 2 megawatts. And, well, nuclear thermal, where you actually have a hot core and you send hydrogen through it, you need at least a megawatt thermal for that. But here's the issue. The U.S. hasn't flown a reactor in space since '65, and wherever Ed Storms is, he knows an awful lot about all of these and their ensuing problems and why LENR might be a solution. The Russians have flown 40 missions in space with reactors. Some of you are familiar how one of them fell down in Canada a few years ago, back in the late 70s, to much concern. And the other problem is that to make the plutonium-238, right now it costs $50 million a year, going up to $100 million a year that NASA pays to the Department of Energy. That doesn't guarantee you get any. Right now they're producing at the rate of micrograms, but they are producing it again. And the other problem is that there's radiothermal generator safety and security costs that exceed $20 million per launch because the United States President has to sign off on that. So you can imagine the levels of CYA that have to be employed before he'll sign it or she'll sign it. So in the past, there have been a lot of things to get there fast. So I'll call your attention, whoops. How do you go? There we go. This device, this is 80 meters. This is 240, almost 250 feet across. It employs laser fusion. It sends a pellet down, and then these lasers bounce off mirrors around here, and they fuse it, and that gives you your drive. This is probably not going to work. Now, interestingly, you heard about the CR-39 that Pam mentioned earlier we use very heavily. This is CR-39 used on the International Space Station. And you see an enormous number of things. A lot of these come in from cosmic rays, but a lot of them are spallation products from the ISS itself. And down here in laser fusion, which is where I began using this a long time ago, 30 plus years ago, you're able to not only tell what the species are, you can tell their energies as well. And again, we've relied on this very heavily. So the current steps, over here we have kilopower, and this test is called Krusty. And in here, we've got a coffee can size of heavily enriched U-235, bomb grade U-235, for those who are curious. And what they've done is they've got, originally this was to have 8 Stirling engines on it. This was fully tested out at the Nevada test site just this past April while I was out in Nevada at a conference on space applications. On the right-hand side, you may recognize this. This is the Hermes spacecraft from The Martian. And it has its own little reactor sitting way over here away from everybody. It has a power budget based on Lee Mason's work going back to 2017. And what's real interesting here is that was a 2.5 megawatt electric machine. That was Prometheus that was designed originally in 2005. All of the mechanical work that was done on this, but then that program was canceled. The most interesting part is that of all of the mass of this thing, the reactor itself is only 13%. So I've proposed to NASA another road. And that road obviously began with the work of people in the Fleischmann-Pons effect, looking at excess heat, tritium, RF fields, magnetic fields, and laser interaction. At the same time, we had the U.S. Navy Spay Pacific, and in particular the work in CODEP, and then a patent that we had issued in 2013. And then we finally managed to get, after 4 years, our digital report out, which also discussed uranium fission. This then led into a resumption of NASA Glenn Research Center, which we started with them in 2012, and that continues on to the present time, where they've looked at everything from gas loading, co-deposition, X-ray, and gamma interrogations, and we've at this point put out over 4 reports, some going all the way back to 1989 by Gus Freilich that some of you know about, where he was looking at a Johnson-Matthey system where he's pumping deuterium through it and seeing heat being produced. We also began working with U.S. Navy Dahlgren, and that work continues. Most of that has to do with 2 things. The density functional theory modeling to find out what is the best combination of materials to make this process work. And then the second one is they've done the co-deposition, and we've now for the first time correlated B field, excess power, and elemental transmutation. The 2 papers that we put out that deal specifically with this was the triple tracks from DT Fusion, which we published in Nachwissenschaft, and it happened to be in the same journal, same month, exactly 70 years after the first paper on nuclear fission was published. We then had another paper published. This one was in conjunction with the DOE lab. So if DOE says they've never heard about this, they've never funded it or anything, before we could get this paper cleared by the Department of Energy, they put a little proviso in there, which is we had to acknowledge the funding document from the Department of Energy that allowed that work to happen. So the pictures that you saw that Pam showed, where you've got tracks and you've got these triple tracks, technique that Pam developed of having 2 different surfaces, one where you focus on the lower part where the tip of the CR39 track ends, one on the surface, combining them into kind of a mosaic. And there's no distinction between the red and the blue. This just happens to be the color coding used that time. But what's interesting is these are indistinguishable from using that accelerator that she mentioned in the earlier talk. And this is all covered in our patent as well. That patent took 6 years to get through the patent office. We very explicitly avoided the word heat. So given, as she said, that you've got 6 MeV neutrons, and this is the fission neutrons, this is what we call the Gini neutrons from green nuclear energy, but there's that N word. Very, very small device. This is looking at the recoil energies from which this could be calculated from. And again, this is showing the cross-section for neutrons. But what to me is more interesting is this is a sample, 2 separate experiments that were run at SRI using the protocol completely independently. And you notice over here on this log scale, we're talking about thousands of tracks. So we've got a whole bunch of tracks that come across. This is what held up the paper being published for 2 years. Because one of our co-authors on that particular paper was sure that what was happening here is these were alphas. But how on earth do we produce alphas over an entire range of energies, going from a couple MeV all the way out here almost to 15 MeV? I was arguing that these are neutrons. We finally in the paper agreed that what these were both. How easy. Turns out the story is Pam found in going through the data further, I did the same, and what you have here is a lithium 3-body reaction. which means now the energy is distributed uniformly. So indeed, these are neutrons and alphas, but these are also alphas all across the energy range.
It's your phone.
Oh dear. Just push the button down so it goes quiet. It's probably my mother. She's not doing well, apparently. Any of you have seen the movie Sneakers? So this is work that was done by Lipson and Rosetsky using, again, CR39, which was multiply etched, and they were comparing the proton recoil between a californium source and ours over the energy range of 1 to 4.5 MeV. And the red is from the CR39 that was run at SRI, and the black ones are from californium. And what you see is californium has a continuum that goes out past 6 MeV. In the range of 1 to 4.5 MeV, ours drops off. So in this band, we have essentially monoenergetic neutrons. That's indicative, again, of 2.5 MeV neutrons from fusion, DD fusion. So if you're going to do anything with these, you have to get down to what are the cross sections. And the materials that I happen to like are naturally occurring uranium, primarily 238, and thorium. And if you look through, if you've got 3 and 15 MeV protons, 2.5, 6.4, 14 MeV neutrons, then what can you do? And what you find out is, first of all, there are many competing channels, some of which will just gobble up your neutrons, and all they'll do is do neutron capture or spallation. If you're after heat, that's no good. On the other hand, neutron fission works equally for both of them, and that's about 1 to 2 barns. It's not as good as you get with thermal neutrons with U-235, 530 barns, but you don't have to make U-235 either. And last, it turns out you can do proton fission if you got energetic enough, which we do, but it doesn't happen very often. The cross sections are absolutely miserable. And so what we've got, we think, is a subcritical fission driven by DD and DT fusion neutrons and maybe a few fast protons. And looking at these, what becomes very interesting when we do this using, get the right button here, there are a lot more triple tracks, implying that we've got a lot more DT fusion going on when we use uranium than when we use just palladium by itself. It's a very significant thing for us. And again, as Pam showed, these are what the fission tracks look like. And what we've proposed is reactor stages that, starting with a 10 watt, no big deal, pressurized D2O, you need basically 3 times 10 to the 10 fissions per watt. So to get 10 watts, we're going to need on the order of 3 times 10 to the 11 fissions. Right now, we're producing on the order of 10 to the 6 neutrons per second continuously. So we've got to step that up. And I'd say that's a hell of a long way to go. Well, there shouldn't be any neutrons there at all. And that's exactly what we told DOE, what was it, 10 years ago, Pam? Once we have that running, the idea is to then scale it up. Now we want to move up to 3 times 10 to the 12 fissions per second. Things become interesting when we get to 1 kilowatt. At this point, we're going to be using an advanced Stirling converter, which we have available to us. We would like to produce from a kilowatt thermal 200 watts electric at 400 degrees C. There's more than a few problems going from here to here. We're also looking at using a helium-cooled primary loop. And this is intended for space. We get to the point we can do this, we want to then scale to 10 kilowatts thermal, 3 kilowatts electric, and then we begin flight testing. This is the umbrella Space Act I have. The beauty of a Space Act is that the first annex allows me to play with these things under these conditions. I can put additional annexes on without going all the way back to headquarters and every one of the mission directorates and getting approval. This approval process to do this took me 2 years. And so if you look through here, we've got everything from evaluating what they need, scaling the power to NASA needs, and then the fun part begins, simulating launch conditions, acoustic and shake tables, vacuum solar hot, cryogenic cold cycling. The reason that I'm at Plumbrook is largely because I can do all those things there, and it's less than a mile from my lab. So this is my lab. This is 6,400 acres south of Lake Erie, Sandusky, Ohio. Any of you know about Cedar Point Amusement Park? It's just a few miles north of us. We've got the B-2 Space Propulsion Facility, which is interesting because we can launch rockets indoors. And in fact, this was developed during the Apollo program. The Centaur second stage was launched in there, and what you do is you maintain it at altitude, vacuum at altitude 100 to 150,000 feet where you would launch it. You then have skirts around the bottom of it, and below it, as that thing blows its plume down, we're pumping 1 million gallons a minute of water and pulling that out to maintain vacuum on the upper part. We have a space power facility. This is, I believe, the largest space vacuum chamber in the world. This was originally designed for the nuclear rocket program. It was turned off by Nixon, but it took half of the U.S. supply for a year of aluminum to build the inner dome inside the concrete dome. So if you can imagine having a 1-foot thick aluminum with a 2-foot wide gap, and then you've got a 1-foot thick concrete dome. So what you do is you pump down the center and the gap together to about 10th of a bar. Then at that point, you pump the inside down to space vacuum. We also have these munition bunkers or igloos, and these are all lined out all through here. These were built during World War II to build the munitions that basically took on the Nazis in Europe. The idea was get it as far away from anybody coming here to take them out, put them on a train, put them on a boat, they go up through the St. Lawrence, off to Europe. But we use these. I've got 3 of these for this program. We've got HVAC in there, we've got a lot of high power, and we've also got the ability to dump up to 100 kilowatts of heat. Most of the work that I've been doing is based on nuclear diagnostics and modeling. So for example, we've got high purity germanium, both using liquid nitrogen and cryocoolers. Liquid nitrogen is nice because the resolution's better, but the cryocooler is a lot more convenient and you don't have to worry about asphyxiating yourself. Lanthanum bromide, sodium iodide, everyone's got those. Beckman LS6500 for alpha and beta spectroscopy. The things that we've put a lot of time in over the last 2 years is developing neutron spectroscopy using liquid scintillators and solid scintillators, doing both time of flight. So by knowing how long it took to get from one panel to the next panel, you know what energy it had, as well as using pulse shape discrimination. Some of the work we've been doing has been in very intense gamma fields on the order of 10 to the 18 photons per second. So we have, in some cases, as much as 12 inches of lead to protect our detectors from the gamma field while we're trying to count the neutrons, the few that make it through the lead scattering off as they go. Again, we continue to use CR39, and we have one of the Tassel automated scanners. Interestingly, the first scanner I ever used was at Georgetown. Turns out that was the first one Tassel in Bristol, England ever sold. The one that I currently have, turns out it may have been the last one they ever sold over the span of 15 years. And then for modeling, we make use of the Los Alamos code MCMP 6.1 and the visual editor, which makes what was otherwise a Fortran dinosaur, which was built on something that began in the 50s and hasn't arguably changed much. We also use GANT4, which was developed at CERN, and it's based on C++. The difference being, in one case, you have these, how shall I say, this almost impossible to read coding sequence that you put in card format versus writing C++ code to knit the pieces of GANT4 together to do what you want. We make use of ANSYS for structural analysis and heat flow, and quantum espresso for density functional theory calculations. So in conclusion, we're building a subcritical core, and the idea is we want to get away from having to use fissile material in space. We're making use of deuterated natural uranium and thorium. We're going to customize it to NASA's needs. We've got to evaluate our ability to operate at high temperature to get high efficiency. We have to comply with UN treaties and the US space reactor executive orders from the president, which at the moment say the only reactor you can fly, fission reactor, has to have enriched uranium. That seems a little strange. You're trying to get away from flying bomb-grade material, but you can only fly bomb-grade material. And we will build on the kilopower program, but bear in mind, the reactor core is only 15% of the mass budget. And so this is where we're heading, back to the future, and you all know about that. But the founding of MFMP, strike The movie, please. Kill the lights, and there is sound.
Wait a second. Well, you're gonna get to vote on it. Okay, you pick the one you think should.
We're asking them at this point.
And you have to pay money.
Yeah, hold on. Now, this is how it works.
I got one.
At this, hold on. It's already thought of, and it's already in the working document that we've got attached to this. We are looking. No.
I have very good arguments. Finish.
Okay. So, what we're asking them to do is, what they're asking to do here is to suggest which experiments should be on the list to vote for. Okay. Then, when they pay as minimum of $5 to be part of the social funding,
Beers.
they get the right to go onto SurveyMonkey and choose the experiment.
You have already thought what I was doing. Great. I think it's a great idea.
And then it comes from the people. You drinking my beer now? He's over there.
Just grab his pitcher. I've got a dark back.
Excuse me. My beer was here. My beer was here. My beer? The beer was. You don't understand what I'm saying. Beer was here. Can I have a small one? Like
It's not two
small ones. All right. I'm going to go
You
for
want to
a
order half hour?
Right. Can I hear your? What's your excuse?
This is why democratic companies don't work.
Attending ICCF.
One man, one vote. My vote. Exactly. Do you know about Robert's rules for parliamentary procedures? There's this great cartoon. There's a guy sitting in a board meeting. He says, "I'm running this meeting by Robert's rules. My name is Robert."
Hey, Tyler, come back. We'll figure out.
There's some things in here that I consider are way too high. They can only be American.
Well, let's.
I live in India.
Well, that's
and the purpose is this to get out
That's
the door.
why you come back.
I need to go for a pee though.
So you guys make your edits?
Don't go away. Anybody have some comments or questions?
I didn't post it on the web, did I?
Somebody might contrast that with what David Secom talked about, ordered, rational. Thank you very much. Bob?
So you talked about subcritical reactor materials. What constitutes that? What kind of neutron gain could you have and still have a subcritical material?
Really, the question comes down to how many neutrons, what's the K value, and where is that? And clearly, in this case, U-238 will not sustain a fission reaction. You can't do it. So we've got to continually provide neutrons to it to bring it back up again. In some ways, this is sort of like what the proton accelerator hitting the spallation log, where you have U-238 or spent fuel around it. In our case, it's the same thing, except we're doing from the inside out.
So if you had a source of neutrons that you could turn on and off, can it not be amplified by the core?
Absolutely.
Why not use one of the tubes made at Sandia where they had the DD fusion in a tube that produces neutrons on command? And my understanding or my estimation is that is for building into nuclear weapons to test them in situ for neutron gain.
Actually, those accelerator tubes are also used in the weapons themselves, but they're used all over the world for everything from oil well logging and things like that. If you look at the power required to drive those, we're typically running them between 50 and 100 kilovolts. You're talking about many, many kilowatts to produce at most 10 to the 12, 10 to the 13 neutrons per second. And they don't have a long lifetime typically. Now, George Miley's done a lot of work on a targetless version of this, and there's a company in now Liechtenstein that has picked up on that. But again, you're talking about a lot of power to drive it. So the question is, how much power do you have to put into that to produce your neutrons to make up for the deficit? I'm hoping to beat that by not having to have that power budget, but doing more or less the same thing.
So you couldn't have a multi-stage device where each stage had neutron gain, because that would not constitute being subcritical?
You could have neutron gain, but the real question comes down to, you look at the cross sections, the slide that I put up there showing all of the competing processes for gobbling up those neutrons. With U-238, they don't go into fission. They typically go into other processes, mostly breeding plutonium.
So is your vision not to have something that has neutron gain?
Not from internally, that's correct.
Okay. Thank you.
And that's why it stays subcritical.
Thank you, Larry.
Okay.